Okay, hey. So what we're looking at is, oh, sorry. There we go. First principles definition for the derivative. Okay, which is effectively a theory. It's about the instantaneous rate of change and how last semester, when we were talking about it in advanced functions or pre-calculus, we were left a little disappointed in the fact that the most we could achieve was just an estimate of the instantaneous rate of change with this formula here. And that's this formula where you end up taking the function, evaluating it at some point slightly in the future in the x value, so sort of down to the right, and then you evaluate it again at the point you're interested in and divide it by that change, which is effectively an average rate of change, not an instantaneous rate of change. But since the x interval is so tiny, then we kind of said, well, maybe it is actually an instantaneous rate of change. Okay. So what I'll do is I'll just do a quick revamp of that. So remember that the instantaneous rate of change was 1/2. Okay. I take the function, remember, and I evaluate it at 1. This is where I'm interested in, x equals 1. But I add to it 0.01. So I'm effectively evaluating this 1.01 squared minus 1. So that's the first part. And then I evaluate it at 1. So I'm going to do 1/2 times 1 squared minus 1. And then I divide the whole thing by 0.01. Okay. And if you look closely at this algebra here, this -1 and this +1 are going to cancel. Why is this positive? Because remember, this negative sign distributes in. So what I'm going to be left with is half of 1.01 squared, which is just a 0.51005. And then I'm going to subtract half of 1 squared. Well, half of 1 squared is half. And then I'm going to divide by 0.01. And I get a 1.005. Okay. So this is my instantaneous rate of change. Okay. Excuse me. So that's kind of the idea there. Now, here I've got a graph that I can, oh, it's up here somewhere. Where is it? Hold on. Where is it? Oh, sorry, guys. I lost that graph. Here, let me click that again. There it is. Here I got a graph that helps us visualize what was happening there. So I've got my function, 1/2 x squared minus 1. And this here represents the slope. And what I'm doing is well, a is the number that I evaluated at. So in this case, it was a 1. I've got that all set. If I want to evaluate it at a 2, I evaluate it at 2, meaning if I want the instantaneous rate of change at 2, then I put a 2 there for A. But I want it at a 1, so I'm going to go ahead and change this back to a 1. This is the amount that I add to go into the future, and then I divide by that same amount. So in this case, I'm doing a 1. We did a 0.01, so a 0.01. And notice my instantaneous rate of change was 1.005, right? And basically what we ended up doing there is if I move in, we went ahead and took a secant line, right? And I put the 2 points so close together that this could be considered a tangent line, right? For example, if I just do a 0.1, then the two lines are pretty close together, but they're not really, that close. They're 1/10 of a unit. away from each other, meaning that I've created a secant line that spans 1/10 of a unit over the course of the function. Okay? And we say, well, that's pretty small. So that could be considered an instantaneous rate of change. And then the slope of this line represents that instantaneous rate of change. But then we thought, well, let's just go more detailed. Let's make it smaller. And that's where the 0.01 comes in. Okay. But then if I zoom in on this, because we're knowing that these functions are infinitely small, look, if I zoom in, these points start to look again kind of pretty far from each other. And so I'm going to say, well, since I've been able to zoom in so close, why don't I just make those 2 points even closer together by making my amount that I move into the future 0.001. And notice what happened to my instantaneous rate of change. It became closer to 1. Oh, because these points are really close together. So I now have a secant line that is effectively, if I zoom back out, it's a tangent line. Look at that. It's not a secant line because I've tricked the computer into, or sort of the math, into going. And as we move, we could even go further and further. We could go 0.00001. And at some point, it just sort of doesn't change anymore unless I zoom fully in here. If I keep zooming in and in and in, at some point you'll see that I actually do have 2 points here. There it is. I do have 2 points here, but they are 0.00001 units away from each other, which is wildly close to each other. And as you can see, my instantaneous rate of change is effectively 1. So we might just say, look, I might as well just say that that instantaneous rate of change is 1. Okay? So that's where the origins of this definition come from. All right? So going back to our notes here, as I zoom closer and closer, we can get a better estimate, and we just get closer and closer to 1. Okay? So there, that leaves us with the next topic. It's like, well, mathematicians were unsatisfied with this over the years, and they're just like, hey, you know what? Why don't we just make a better definition? So they said, we're going to take this formula, we're going to rewrite it, but instead of putting a 0.01 here, we're going to put an h, just some variable, so that way the user can basically make it as close to as small of a number as possible. And somebody else thought, well, look, why don't we also put a word up here that says, hey, everybody, this is the best, the most effective, if you effectively make this h as close to 0 as possible. And you might say, well, how close to 0 can we get? Well, the idea is to get as close to 0 as your mind or equipment can achieve effectively. And so we're going to do that. All right. So now, if I go ahead and apply this formula, this new and improved formula, where we're allowed to make this value as close to 0 as humanly possible, then I'm going to reapply it to our formula here. So let's go ahead and do that. That means I'm going to do the instantaneous rate of change. Oh, and by the way, they called this f prime. It's got a special name. Okay. And then this is called the first principles definition. Okay. It's one of the fundamental definitions of calculus. Okay. So now that we've got this, we're going to say, all right, let's go ahead and apply this definition to this function and see what kind of instantaneous rate of change we can get. Based on our previous example, we're going to expect 1 to pop out of here, right? Because the smaller and smaller I got, the closer and closer to 1 I got. So let's check this out. So first off, we have to kind of figure out how to use this. So notice that this is f of x. This first part is f of x evaluated at x plus h. Well, f of x is here, so I'm going to write it down, but I'm going to evaluate it at x plus h. So that's 1 half x plus h squared minus 1. And then I'm going to subtract f of x, which is 1 half x squared minus 1. Okay? So if you're looking closely at this section right here is this thing, and this section right here is that thing. Okay? And then my minus sign is right there. Okay? And then don't forget I have to divide this by h. Now, a lot of people would say, all right, well, now what we're going to do is we're going to let, oh, shoot, I forgot my limit as h approaches 0. Classic mistake. Okay. Don't forget that we need to write this, the limit as h approaches 0 of f prime of x. Okay. And now we're going to say, all right, let me go ahead and make h effectively 0. Well, if I make h 0, then I get 1 half of x plus 0 squared minus 1 minus 1 half of x squared minus 1 over 0. And if you look closely at this, you end up getting effectively 0 over 0, which is like, oh man, what the heck is 0 over 0? So we have a bit of a problem where if we let h approach 0 immediately, right at the beginning, we get some sort of nonsensical value, because what is 0 over 0? Okay, we don't know. So we're not really able to figure that out in the moment. So rather than letting h approach 0 immediately, what they say is, look, let's do some algebra and see what happens. This is, by the way, called a limit of indeterminate form when you get a 0 over 0. So I'm not going to let this approach 0 just yet. I'm going to do some stuff. So I'm going to take 1 half x squared plus 2x h plus h squared minus 1 half x squared plus 1. I'm just doing some algebra in the numerator, right? So you might be saying, well, what's going on there? This part, x plus h squared, is this. I just expanded it using FOIL, right? And then over here, I went ahead and distributed this negative sign into here, and I got a positive 1, right? A negative 1 and a negative out front become a positive 1, okay? Now this 1 half needs to distribute into here, okay? So I'm going to go ahead and do that. So f of x is equal to the limit as h approaches 0 of 1 half x squared plus, well, half of 2 is just 1, so I'm going to leave that as xh plus 1 half of h squared minus 1 half x squared plus 1. All of this is over h. And so if you notice, there's some stuff that cancels. A 1 half x and a negative 1 half x cancel. A 1 and a positive 1 cancel. Okay, so I end up with this, right? I think I said negative. I said that wrong, but it's a negative 1 and a positive 1. They cancel. So let's clean it up and see what we're left with. X h plus 1 half h squared over h. Oh, this is nice. There's practically nothing left here. Okay, so let's keep an eye on this. Now, the thing, I've got some h's that I guess I've got a common factor of h. So I'm going to factor out an h. So I've got this equals the limit as h approaches 0 of h times x plus 1 half h over h. And look at this. I can cancel that h with that h. And look, this h is now gone. And at this moment, that zero that was happening in the denominator up here, this zero that I'm pointing at right now, is that zero is no longer a problem. And so I might be able to now see what happens. So this is equal to the limit as h approaches 0 of x plus 1/2 h. Okay? So now I'm going to go ahead and I'm going to try and let h approach 0. Okay? I'm going to let h approach 0. So if I do that, I end up with x plus 1/2 of 0. Right? I wrote the word 0 because it's not the actual number 0, but it's like effectively 0. It's so close to 0 that it's about the smallest we can get. So in the end, the derivative, or the instantaneous rate of change, is effectively equal to x plus 1/2 of the smallest number that you could possibly think of. So since that means that the instantaneous rate of change could be considered x plus the smallest number that you could effectively think of. So you know what? I'm just going to say that this is the instantaneous rate of change. Okay? Now you might be saying, well, wait a minute. How do we use this? I thought we were supposed to get the instantaneous rate of change at a specific number, 1, right? At x equals 1. But that's true. It turns out this formula here that we've just built will give us the instantaneous rate of change at any number we want. Well, since we're interested at x equals 1, let's go ahead and now evaluate this at 1. And so I'm going to say that f prime of 1 is just 1, meaning this is the instantaneous rate of change at 1. And if you recall from our previous example, we were expecting to get 1 when we got this, when we solved this whole thing out a few minutes ago. Okay, so that's kind of basically the idea in our first principles definition. Now, this looks like to be a lot of work, right? So you're going to want to work on this and practice it a little bit. It's some algebra, but it's very repetitive. Things always cancel in this area. You generally, oftentimes have to expand. Oftentimes, well, almost every time these h's cancel in some way or another. Okay, and then you're left with something very, very simple towards the end of the question. Okay, so anyway, that's kind of the idea. Notice in the following graph that when we use this, our new definition, rather than the old definition, okay, when this one is used rather than this one, we can successfully define a tangent line rather than a secant line. So here I'll show you. What I've done is I've made a similar graph where I've got it at 1, and no matter how far I zoom in here, there is no other point. Okay, so basically, if I end up using this new thing called the derivative, which is this right here, this is another way of writing derivative, d dx, I can effectively get a full-on tangent line represented. And notice what's the slope of this tangent line? 1. Look at that. That red line has a slope of 1. If I move up 1, the rise is 1, the run is 1. Okay? So that's kind of the idea there. All right? So this is a very key concept. It's going to take us several months to fully develop. Okay? And then we're going to start to use it to discover and solve all sorts of extremely interesting application questions. And the power of this concept is, well, difficult to fully explain in a single video. So, well, possible actually. So Anyway, notice that they'll after we do this over and over again. So after we use the first principles definition over and over again, we're going to start to discover that there's actually patterns here that we can exploit, and we're going to soon learn that we don't actually have to apply this definition over and over again anytime we want to take a derivative. We can make some assumptions, exploit some patterns, and develop a set of rules that allows us to take derivatives or find instantaneous rates of change of functions that are highly complex. And we can do that with just a few quick rules and things like that. So by the end of the semester, you'll be able to find the derivative of something crazy like, uh, 3 sine to the fourth uh, x minus pi times whatever the natural log of 3x to the third or something, right? So we will be able to um, find the derivative of this pretty easily. And note, we're not going to have to take this and plug it into here, into this formula, and do some wild algebra. There'll be some really quick and easy rules that we'll learn. Okay, so this is the introduction to the instantaneous rate of change and the derivative there. Okay, very nice. Um, where's my video? Oh, here it is.